Hello, thank you for coming to my talk. Today I'll be presenting SafetyNOT on the usage of SafetyNet Attestation API. So many Android applications provide security sensitive functionalities like handling private information or providing paid content to their users. But Android apps and devices can be tampered by attackers who can access the private information or gain access to premium content without paying any cost. That is also the threat model for our paper, that an attacker has the capability to tamper an application, which they can do by repackaging, or tamper a device, which can be done by rooting it. However, we assume that the attacker cannot mess with the SafetyNet API, which is supposed to prevent this tampering. So an attacker can tamper an application by repackaging it. Repackaging involves decompiling the APK into smally, modifying the code, and then repackaging it again. Another dynamic approach of tampering an application is to hook its functions during runtime and then inject code to get the required functionality. Devices can be tampered by rooting the device by using a rootkit, or they can be tampered by installing a modified ROM. Applications try to detect these tamper mechanisms by attackers by either checking the bootloader state of the device or by checking for presence of rootkits. But these checks by applications can be bypassed by attackers. So Google provides their own anti-tampering API called SafetyNet Attestation that is part of the OS, and it performs various checks to assess the integrity of the device outside the application, so that the developer does not have to implement these various checks within the application. SafetyNet performs several checks to assess the integrity of the device. Two of them are listed over here, like checking for the presence of rooting techniques, which includes like looking for SU binaries and checking if the official OS distribution is installed on the device. Application integrity can be checked by extracting the APK hash and then comparing it with the hash that was uploaded to the Play Store by the developer. If they don't match, it means that the code of the APK has been modified. So on the Android device, the SafetyNet attestation has two main components: the client app and Google Play Services. Client app is the developer's app, and Google Play Services runs a background process which we will call the GMS process, that is responsible for various functionalities of the Android. So in the client app, the developer has the application code from where the developer can use the SafetyNet Attestation API by calling the attest function. The attest function takes two arguments, a nonce and an API key. When the attest function is invoked, the call is handled by GMS client library that is provided by Google, and it is also present within the client app. When the GMS client library gets the call by attest, it performs an IPC to the GMS process. When GMS process gets the IPC, the GMS process performs various integrity checks on the device and the client app and sends that data to the Google server. As mentioned before, Google provides the SafetyNet Attestation API as a unified solution for checking the integrity of the Android app and the Android device. Since the API is supposed to check the integrity of the app, the verification of that integrity cannot be done within the app itself, and it has to be done on a remote backend server. So the developer has to use a remote attestation protocol in order to use the API correctly. Specifically, the steps are as follows. First, a nonce is generated by the client server and it is sent to the client app. Using this nonce, the client app invokes the attestation function. Then the GMS process handles this call and performs various checks about the device integrity and the app integrity and sends the data to Google server. The Google server analyzes this data and sends back attestation data to GMS process. Now GMS process sends this attestation data to the client app. This attestation data contains a SafetyNet JWS which is signed by Google server, so this JWS cannot be tampered with. This JWS contains information about the integrity of the device and the app. The client app has to extract this JWS from the attestation data and send it back to the client server. Now the client server can perform verification of this JWS and assess the integrity of the client app and the Android device. So the goal of our paper is to see how this attestation API can be misused and how real-world applications are using this API. For that, we develop our semi-automated analysis framework. So we analyzed the API systematically and found various ways in which the API can be misused. 3 of them are listed over here, like nonce generation, handling of the SafetyNOT JWS, and incorrect or incomplete verification at the client server. The rest of them are in the paper, and you can find more details about them in the paper. I will be explaining only 2 of them. So nonce generation. The correct usage involves that the server generates the nonce and sends it to the client app. But applications can also generate the nonce locally, which makes the attestation vulnerable to replay attacks. To perform a replay attack, an attacker just has to extract the SafetyNet JWS from a device on which the SafetyNet checks pass, and then the attacker can replay it on a device on which checks fail, and the server won't be able to see if the JWS has been replayed because the server doesn't know what nonce the JWS corresponds to. So for the SafetyNet JWS, in order to handle it correctly, you have to send it to the server for verification. But some apps can try to verify it locally on the device within the app code. But these verification checks on the device can be bypassed by attackers by repackaging the app or by hooking the verification functions and circumventing them. For example, an app that has hard-coded the verification checks within the application, as seen on the left, if the SafetyNet checks pass, the app will continue executing, otherwise it will terminate. An attacker can repackage the app and set the if condition to be always true, so the app always continues executing and never terminates. So our analysis had 4 main steps. First was the collection of APKs from the Google Play Store. Once we had the APKs, we analyzed them statically to see if the application has SafetyNet code or not. After that, we analyzed the application dynamically to see which applications are actually invoking the SafetyNet code. After we have the applications that we know are using the SafetyNet API, we analyze them manually to see if they're using it correctly or not. So for static analysis, we identified some keywords that are always present in an app that is using the SafetyNet code. To find these keywords, we disassemble the APK into Smalley, and then we perform string search on it. If we find these keywords, then we assume that the application has SafetyNet code. On the applications that we think have SafetyNet code, we need to see if they are actually calling the SafetyNet API. For that, we identified some functions that are always called when the SafetyNet API is invoked. We hook these functions and we install the Android app on the device. We run the app and we see if these functions are invoked during runtime. If we see the invocation, then we assume the app is using the SafetyNet API. So after we have applications that we know are using the API, we reverse engineer them manually to see if they are using the API correctly or not. So we use various techniques like decompilation, dynamically hooking functions, and network sniffing. So decompilation is our static way of analyzing the code. We look at Java code and see if the app is doing local checks or generating the nonce locally. Dynamically, we hook functions, look at stack traces to see how the application is working. We looked at the function arguments of the functions we are interested in, and also we could confirm our findings from static analysis. By sniffing network packets, we could see if the nonce is coming from the server, or if the SafetyNet JWS is being sent correctly to the server, or how the server is responding to different JWS. So in total, we had around 163,000 applications downloaded. After doing static analysis on them, around 20,000 of them were left that we thought had SafetyNet code. After analyzing them dynamically, there were only 64 applications that actually invoked the SafetyNet API. After manual analysis, we found that all of those 64 applications were misusing the API at least in some way. So this graph shows the distribution of misuses that we found in the applications. As you can see, the most frequent misuses was local checks. That corresponds to applications performing verification of the JWS within the app instead of sending it to the server. The second most common was no error handling. That corresponds to when the SafetyNet API fails to perform attestation correctly, the app has to handle that case, but some apps were not doing that. So an attacker can always cause the API to fail and bypass the checks. As you can see, that some of these applications is more than 64 because we found that applications were messing up the API in more than one way. For example, there was an app called Geon that provided users with rewards after they had performed certain tasks. This app was misusing the API in three ways, like it was generating the nonce locally, it was performing local checks, and it was not completely sending the JWS to the server. After we had found applications that were misusing the API, we wanted to see if we can actually bypass these checks by exploiting their misuse. So by testing the applications on different devices, we saw that some applications behave differently in a tempered state by showing error messages or by terminating after launch. There were 33 out of those 64 applications. We tried to prevent this behavior change, like the showing of error messages, by circumventing the SafetyNet checks. We exploited our found misuses to bypass the checks in 21 out of 33 applications. In some applications, the behavior change was not prevented because these applications were using alternate tamper detection mechanisms in addition to SafetyNet, which were mostly implemented in native code or reactive code, which required more reverse engineering to be bypassed, but in theory, they can also be bypassed. So the main limitation of our static analysis was obfuscation, because we were using string search to find the potential usage of SafetyNet code. Obfuscation can hide those keywords and our analysis won't be able to detect the code. But since most applications use the default Android ProGuard obfuscation, which does not obfuscate the keywords we were looking for, we assumed that our static analysis was robust. So the main limitation for our dynamic analysis is that some applications might be calling the SafetyNet Attestation API, which is not triggered by our automatic interaction. But as Google guidelines state, and as we have seen in many applications, the API is usually invoked at launch time. So we assume that our analysis can cover majority of the cases. So in conclusion, we performed the first large-scale semi-automated analysis of the SafetyNet Attestation API. We identify the API misusage in real-world applications and circumvent their checks in majority of the applications. Thank you for coming to my talk. You can find more details about the analysis in the paper. If you have any questions, I will be happy to take them now.